So next up we have linear approximations and differentials. And I kind of was wondering why this section was important, but it is necessary if you want to be able to find values for something like, I don't know, the square root of 3.7. It gives you an actual numerical value that's closer to just kind of guessing, right? As a mathematician, I can sort of tell you that if I wanted to know what the square root of 11 was, I would just simply um, take the fact that the square root of 11 is between the square root of 9 and the square root of 16, which is 3 and 4, and then I would kind of guess, oh, well, it's closer to 9, and I'd say it's probably about 3.2 or something like that, and that would be my approximation. Well, this gives us a way to approximate over, and it gives you a interval in which will contain the value of that approximation. So you should have the square root of 11 being being contained inside of some interval that's relatively close to that value. And so that's where this is kind of like what this is important for. And so linearization is necessary because linear functions are particularly easy to deal with in comparison to curves. Sometimes we can't even deal with curves as they make determining a points near f of a difficult to find. And so I guess, if you think about it, if I ask you what the square root of some number is, that's, let's say I give you 1 over the square root of 2. Let's look at that real quick, just so I can be clear what we're doing. If we have 1 over the square root of 2, you won't be able to tell me what that is, but if I asked you what 1 over the square root of 4 is, you would tell me, oh, this is 1/2. Okay, so you'd know that's 0.5 or whatever. But to get the square root of 2, we know that it's 1 point, some weird approximation. We could actually plug that in, but you don't necessarily, because you're going to approximate that value. It's nice to just have an interval in which you can kind of know that you're going to have the value somewhere in there, and it's going to be closer than what you'd get by just simply approximating to 3 decimal points or something. So the linear function whose graph is tangent line is called the linearization of f at a. So this equation, I noticed something, is literally just the following one. If you have y minus y1 is equal to mx minus x1, and you just replace f of a and a with those values, right? Because a would just represent x and y would represent f of a. Then you're looking at the point slope formula, and all they've done is solve for y. So they go, oh, y is equal to y1. Actually, they use plus. So maybe, oh no, this is right. Plus mx minus x1. Okay, and so that's just an observation I made. It's not really that hard of a formula to remember, because if you know this one, then you can clearly get that. So with that being said, let's look at a problem. It says find the linearization of the function square root of x plus 3 at a equals 1, and use it to approximate the numbers 3.98 and 4.05. Are the approximations overestimates or underestimates? And so if we want f of x is square root of x plus 3, so let's find the derivative of this. This is x plus 3 to the 1/2 power, which is equal to, if we take the derivative, 1/2 x plus 3 to the to the negative 1/2. Okay. And now this is equal to 1 over 2 square root of x plus 3. Okay, so that's that. And then we can kind of figure out what f of 1 is and f prime of 1. So if f of 1 is equal to when you plug in 1 into this. So that would give us 2, right? Because we'd have the square root of 1 plus 3, which is equal to 2. And if we have f prime of 1, this is going to equal this value when you plug 1 into this, which is going to be 1 over 2 times the square root of 4, which is equal to 1 over 2 times 2, which is 1 over 4. Okay, so there's 2 values. Okay, so now let's use these values in that formula, this one. Okay, so we've got f of a being equal to, so we've got the linearization of x being equal to 2 plus 1/4 x minus 1. Okay, that's their values. And so if we go from here and distribute this stuff out, we have 2 plus 1/4 x minus 1/4. Okay, 2 minus 1/4 would be 7/4. Plus 1/4 x. So that is our value. Okay. Now, remember, we want to find the square root of 3.98 and the square root of, it said 4.05. Okay, so what we would do is we have, we're just going to take this part of it. We have 7/4 plus 0.98 over 4. And that is going to equal, let's see what it is. 7 divided by 4 plus 0.98 divided by 4. 1.995. Which is about right, correct? Because it should be about 4. And then same thing here, we're going to do it with the 0.05. So 7 over 4 plus 1.05. And then this is going to equal 0.05 divided by 4, 2.0125. Okay, I think there was one other part to the question. It said, are these overestimates or so to do that, you'd have to actually graph it, and we will in just a second. So a calculator would obviously give us approximations of this, but this gives it over an entire interval. That's what the advantage of this is. And so let's go and graph this on Desmos. We have y is equal to square root x plus 3. We have y is equal to 7 over 4 plus x over 4. And so from this graph, if you notice the blue line, which is our tangent line, is over it's on top of this curve. And so because of that, it is considered to be an overestimate. Obviously, if it was below it, it would be an underestimate, and so on and so forth. So I hope this helps, guys. Make sure that when you go to practice these, you check your work. I'm sure you can find it in the back of the book to verify if you're doing them correctly, or you can always ask for help too. So thank you guys for watching. More videos are coming.